Welcome again, MMI711 sequence models in multimedia, and this is week 5. This week we are going to cover CNN plus RNN architectures. Actually, this is a special type of an architecture, which you can see my screen, right? The slides. I should have checked it first. Yes.
Yes, teacher.
Thank you. So this CNN plus RNN architecture is a special type of architecture because it is the type of architecture which we use to model spatial signals which have sequence nature. So you have a sequence signal which has spatial components. In that case, what you do is you first use a CNN to get the abstract features, then use the RNN to model the sequence. So it is like combining convolution plus recurrency. Remember, when we were covering different types of LSTMs, there was a conv LSTM. Remember? The conv LSTM was type of an LSTM which also had a type of convolution capability and recurrency capability. Conv LSTM from the previous week. However, in most problems, this architecture seems to be better because what we're trying to do is we are trying to model the architecture in a discrete fashion. First, the CNN extracting the spatial features, then those high-level representations as a part of a sequence fed to a model with recurrency, a recurrent neural network. And actually, it is widely used. It is like a very common tool in today's deep learning. And it has been like 5 years people started using it, but today it is like a very common tool. It's like the SIFT of 20 years earlier. So people use it today. So what we're going to cover is convolution plus recurrency. Very briefly, convolution allows us to learn spatial dependencies. What is in your signal and what is the spatial relations between the signal. And you, by using convolution and by using that relation, you carry this signal to a higher level of representation. Whatever the type of your signal is, it could be an image, it could be sound, is going to be earthquake signals, the type of signal that we are working on, as I've always mentioned, or it could be any other type of spatial signal, which the sensory information is along a space continuum in a dimension, like, I don't know, frequency, or it's pixels, or whatever it is. It could be anything. A time series also has a spatial continuum. So, but with convolution, we get the abstract features. With recurrency, we learn the sequence model, and we get the dependencies within the sequence, in the sequence dimension. So what we do is, actually, we use an architecture that has a CNN first, then serially connected an RNN later, together for spatial temporal signals. Yes, we can. So it is like input frame, output frame, but this is like input video, output tracks kind of. So it is track, could be anything. It could be a tracking signal, or it could be an indicator of what's going on in the video, like an action recognition. Actually, action recognition is a very good example for CNN+RNNs. So what I'm going to be doing this week is I'm going to be covering CNN plus RNN architectures in the literature. I hope this is going to give you an idea about your studies and things that you may apply to this from your thesis, for example, to this idea. So input with spatial structure like images, audio, whatever, cannot be modeled easily with the standard vanilla LSTM. Why? Vanilla LSTM can extract sequential dependencies, or that's right. However, the spatial input signal is usually in a very raw format. It is a raw format signal. There are pixels. What we have to do is we have to just carry it first into a higher representation. So recurrent and convolutional networks can be combined in different ways. And what we're talking about today is a CNN plus an RNN architecture. So serially connected. The basic that you can think of, the simplest model that you can think of. Okay. There are other types of architectures that you might think of. Well, you may see them in papers and different designs. Today, we are going to be covering very simple CNN plus RNN architectures because it is actually the first model of a spatial encoder, temporal decoder model that we are going to be covering. Because in the following weeks, we are going to cover encoder-decoder architectures, which is like the fundamental architecture in machine translation and other sequence models. Okay. Things that we have already covered. So is what we are going to do is we're going to use high-level features obtained from a CNN and we are going to feed it to an RNN. Okay? CNN and afterwards RNN. Very simple. That's what we're going to cover. And this simple idea is capable of many things we are going to see. So the first idea was, the earliest idea was actually in 2014. It was by Andrea Carpati and Fei-Fei Li, the famous people from the Stanford lessons. I'm sure you've seen Stanford CS 231 deep convolutional neural network lectures in YouTube. Fei-Fei Li, Carpati was a postdoc of Fei-Fei Li. They were working together by then. And Carpati was always amazed by the work of RNN. So what they did was they have constructed a very simple CNN plus RNN architecture. The CNN was VGG. The study is that old. Imagine you're using a VGG, I mean, because VGG is like the most primitive CNN architecture that you might think of. Today we have much better ones. I mean, this is one of the early studies. That's why it's so that is why it used VGG, and then RNN. Not even an LSTM, an RNN. So it was like the vanilla CNN RNN architecture, and it had some fantastic results. Kind of results that they didn't get up to now in image captioning. So what they did was they captioned images. We are going to see it in a couple of minutes. And it was a simple RNN with 512 neurons. So the study was, you get an image, you get a VGG, pre-trained VGG. You obtain the features from the final layer, which is a fully connected layer. Then you feed this final fully connected layer as a state to this RNN. Okay? And you don't feed an input. So it is like an inputless RNN. And what you had was, you have fed the output of the first sequential input to the RNN as the next input. So it is like you're feeding it strobe and strobe. So it is like you have an RNN here. You are feeding the first one, then you're feeding the next one, and next one. What you have is a very simple architecture. So let me just put it this way: strobe, strobe, hat, hat, hat. So in the end, the output words are words. The output, actually, these are numbers. These are some vectors. Those vectors are mapped to some words, which is called word embedding. If you're into some sort of natural language processing, you know what this is. So what you do is you construct sentences. And actually, they have done very, very nice things with it. So the data set is like you have a training image. And the input signal is a tabby cat is leaning on a wooden table, comma, with one paw on a laser mouse and the other on a black laptop. It's a very strange image and it's difficult to learn. So what they fed was, they fed the image to this VGG. Then during training, what they did was they fed the words one by one. And they wanted the RNN to output the next word of the sentence. And the loss is constructed accordingly. Nothing else. So it's a very simple idea. If you have a word embedding, which converts each word in your vocabulary to a vector, and if you could calculate the distance of a vector from another vector, which is a complicated business still related to NLP. If you have taken an NLP course, you know what I'm talking about. There are different measures for distances between words. If you haven't taken an NLP course like Tuba Hoca's course, in the following weeks, we are going to cover distance, the meaning of distance for NLP, because in CNNs, we cover distances as for example, Euclidean distance between high-level features, the output of a CNN. However, for text, this is different. In the following weeks, we are going to talk about this idea of word embedding, carrying words into some vectoral definitions at an introductory level, but it will be enough for you. At this point, let's not delve into this. Let's understand CNN+RNN architectures and how word embeddings and vocabulary is theoretically used here. Then we'll see them practically in future. And plus, today, in the second hour, I'm going to be going over a code, which is a live code for an image captioning algorithm. There we have a simple version of a word embedding, not a complicated version as we use in machine translation, which we are going to cover again in the following weeks. So this week is kind of the week you'll get used to understanding how words are represented as vectors in space at an introductory level. I mean, if you already know it, because I know some of you do. For example, Ozan is doing his thesis on this stuff, so he's much prepared for such business. But if you're not, because some of you are working on only vision signals, this will be the first time you're going to see it today in the live code. I get back to my slide. So the idea is we have some sort of data like this. We feed the data and train it. And in the end, we test it. So these are tests, validation results, guys. So in general, let's go over the results. And I'm going to actually, in the second hour, when I'm doing the live code demonstration, I'm going to run a more sophisticated version of an image captioning algorithm. And I'm going to show you a lot of results and in the chronological order of the training. So I mean, and validation constructed in early training, then next and next. So you're going to see the evolution of training, iteration or iteration. But let's go over this very simple example. This is Andrea Carpati. If you've seen the videos, you know him. And I remember him saying in one of the lessons exactly this sentence. He's saying that RNNs has some fantastic power if you can feed high-level features to them. Whatever. Let's get back to results. A man in black shirt is playing guitar. Fantastic result. But it's a very simple sentence. Sorry, it's a simple image because the entire image has two distinct high-level features, a man and a guitar. But the algorithm is able to construct black shirt as well. A man in black shirt is playing guitar. So using three features, you obtain it. So construction worker in Orange State West is working on a road. It is not a road, but it's a good result. Somehow the algorithm thought it was a road. Two young girls are playing with Lego toy. This one is not young, but the original CNN used in this network, which is VGG, was not trained to estimate the age of a person. That's why somehow it mistakes the age of the person, says this is young. I mean, if this lady is young, I wouldn't say that this lady is young either. I mean, I wouldn't call her old. I'm not doing ageism, don't worry about that, but I wouldn't call her young. So a baby and her carer is playing Lego, I would say. But still a good sentence because it's getting the features. A boy is doing backflip on wakeboard. A fantastic result because it understands backflip. So in general, network generates very accurate and sensible description of images. In these examples, there are some results. This is not a wakeboard, but the flip is correct. And two young girls is wrong, but still, what it does is it can extract features and construct a sequential sentence. I'm going to go over some samples of this very early idea. This is very important, guys, because it's the simplest one. You're using a VGG and RNN. You couldn't make it worse. I mean, anything you change in this algorithm, this architecture, will make it better. I mean, use, I don't know, residual nets instead of VGG, it's going to be better. Use LSTM instead of RNN, it's going to be better. Use an advanced RNN like Elman instead of CNN, vanilla RNN, it's going to be better. So it's like the very basic, I don't know, thing to compare. So that, I think that's why it's kind of logical to get over it first. So the first description of man in black shirt is playing guitar does not appear in the training set. However, man appears in the training set, shirt or black shirt appears in the training set, and guitar appears in the training set. So somehow this shows us the capability of what RNNs can do. They can do two things when trained with enough data. They can construct a grammatically sane sentence logical, reasonable sentence, like man in black shorts playing guitar. That sounds like proper English to me. Second, it can properly use the features it could extract from the image, grammatically and semantically correct in a sentence. But if it cannot extract those features, because some abstract features are difficult to get, just like the comparative age of this lady. I mean, calling them both young is not wrong, but it's not entirely correct, because in the context, you wouldn't call this lady young when you call this lady young as well. Anyway, so we can easily see the capability of CNN+RNN. I'm going to delve into this kind of analysis when I show you multiple examples of the results of a more advanced image captioning algorithm in the live code in the next hour. So therefore, we could say that this simple network could learn how to combine these and generate some meaningful result. This is fantastic, guys, because before this architecture, simple architecture, 2014, we didn't have a model like this. I mean, it was a dream to construct sentences like these from any image. And this successful, because I know there are wrong things, false sentences, but still, this is like a revolution as well. However, although the results look very impressive, there are limitations on the network. I mean, when you read their paper, when you read any paper, they always talk about the best results they have. They put their false and inadequate results as well, but it's not enough to understand it. So what I recommend always is, if you're interested in a study, get their code, rerun it, rerun the validation, visualize every validation result, and try to understand the capability of that model. This is what I've done already. I'm going to do in the next hour. So get ready. So this is one of the pioneering studies, this one. So Karpathy FFAL. Actually, after this study, the field of image captioning was flooded by various CNN+RNN architectures. Because imagine in 2014, with this knowledge of yours, you have seen this study. We would first think that let's use a better CNN, let's use a better RNN, and just do the results. People have exactly done that thing. So one of the famous ones is show and tell. It's still very famous today. I mean, if you're doing some sort of image captioning or visual question answering thesis or study, you come across show and tell. This is the first thing that you come across, because this was the first idea. This was the first real mature implementation. It's from Google, and as you can see, these are very famous guys. Oriol Vinyals, I love that guy, because he's the guy who is working on AlphaStar. AlphaStar is the Google DeepMind StarCraft player, if you have seen it. It's fantastic. And this guy is also a very competent StarCraft player as well. So that's a very good team. Whatever. So they come up with this model. The model was very simple, guys. Just like I told you, they changed the CNN with ExceptionNet, which is the Google net, which is by them the Google version of VGG. VGG was from Oxford. Google had ExceptionNet. ExceptionNet was not like a serial network. It was more like a directed acyclic graph. It was trained differently, and it was very powerful as well. However, more importantly, what they did was they used an LSTM instead of an RNN, so that they could train longer sentences. That's why this model is more capable in using, in constructing longer sentences from images. However, today we are doing these kind of things with transformers, which we are going to be covering in the following weeks. Whatever. So this is the evolution of what is happening. So the same, deep vision CNN, you're generating an RNN, and you're generating sentences. A group of people shopping at an outdoor market. There are many vegetables at the fruit stand. Since this is an LSTM, it does not necessarily create a single sentence. That was one of the beauties of their model. So this is their LSTM. This is just an LSTM, actually nothing else. And what they had was this GoogleNet. If you're familiar with different CNN architectures, when you see this figure, even at this resolution, you know that this is ExceptionNet. You cannot see it. Well, let me show you. Yes, because in the video, you're going to see my face here. This is the architecture, and you have GoogleNet here. As you can see, the GoogleNet is a strange non-serial network, but it was their networks. They're from Google. These guys are from Google, so they wanted to use their own network. So you might easily see that this architecture is appropriate for problems that have spatial structure in their input, such as the 3D structure of pixels or whatever, and have a temporal structure in their input as well. For example, it could be images or words to be created, because the sequential structure in an image is like the features alignment in an image, because by the features alignment, we get a semantic meaning, we construct the sentence. Good. Sorry. Okay. Actually, this is the study that we're going to be covering today. And I'm going to be covering this example because I've checked for different implementations in GitHub. And this was one of the best because they used, you can use different type of CNNs. And the original implementation here used residual nets, 34 layers, which is much stronger than GoogleNet or BGG. And you can change the RNN as well. I mean, they've made it, they have a model architecture. You can try GRU or LSTM. So it is like early CNN models for image captioning test bed. It's fantastic. We are going to cover it. Actually, I've run results over it, and I've visualized all the results, and we are going to go over the code, how the basic vocabulary is done, how the basic word embedding is done, and how the code generates some results. And we're going to cover iteration by iteration, the evolution of the training, so that we get an understanding of what it can and cannot do. And this code is fantastic in a way that you can easily use it to apply it to another problem. Imagine in your project, you're going to do some sort of Instagram comment bot in Turkish. You can collect Instagram Turkish comments with high likes from the internet, from the web. Then you can apply it to this code very easily if you create the necessary format of input, which I'm going to be talking about as well. So this is like a nice start for a project of a CNN+RNN, especially if you're not coming from the NLP background. Because if you're not coming from the NLP background, this is a good place to start for you, this example. We are going to do it in the next hour. So in this hour, I'm going to show you different examples of what CNN+RNN architectures can do in different problems, actually. Since many of you are coming from engineering or more interdisciplinary fields, you might realize that there is a problem of CNN+RNN nature that you can easily implement in your thesis. Maybe your thesis is already a problem which is born to be a CNN+RNN architecture. Maybe. So that's to make it more, easy for you to understand. We're going to cover some examples of CNN+RNN architectures. So this one is speech motion recognition with data augmentation. Actually, I'm personally working on this stuff as well. I'm working with a company in Izmir. They're actually a Google Ads company, but they have many operators. They have a call center. There are 50 people working for them. And what they want to understand is if there's a, discussion or something bad word is happening or something wrong going on in the conversation. And they have terabytes of data. That's why they're trying to build up a model like this. So we are using a CNN plus LSTM like this. And this is one of the early studies of it. It is from 2018. So what you have is, you have a sound signal. What you do is, usually in sound, you extract a feature. So most of the sound processing deep learning systems are not end-to-end. This is important, guys. If you're from our department, MMI, you know what spectrogram is, you know what a malfrequency band is, because you have taken Hüseyin Hoca's compulsory course. In sound processing and deep learning, the first thing that you have to keep in mind is, we do not feed the sound signal directly to a CNN or an LSTM. We first do some sort of time frequency representation, like a spectrogram or a capstone, like MFCC. In these kind of representations, the nice thing is you convert a part of the signal to a 2D representation, where usually the x-axis is time and the y-axis is the frequency. So it is like at this point of this time point of the sound signal, we have these frequencies powerful and some other frequencies less powerful, and it goes. So you take little pieces out of it, and you have your signal, which could be a sequence signal. So it is like, imagine you take some constant pieces, like 3-second pieces of spectrograms, and you feed them to first the CNN to abstract high-level features. So it is like the CNN will give you necessary high-level features, like what could be necessary high-level features in sound. There's a laughter here, there's a high-pitched sound here, there's a silence here, there's a music here. Combining that information, in the end, the LSTM can make a sense of that sequence. So it is a laughter, then sound, then music. But I would think that operator is not doing its job. But if it's a conversation in some frequency, which is, I mean, regular speech, I would say, then it may sound like a proper conversation, kind of, if this is my problem. But in this problem, what they solved was speech emotion recognition. So when you're speaking, you could be speaking sad, you could be speaking joyful. It's very easy to understand for humans. So maybe it is inside this frequency band, because when you're about to cry, for example, when people are about to cry, when they're very sad, they carry a sequence of changes in their voice. Maybe you could just learn this in this representation. And it's a very simple model, a spectrogram, a CNN. They have some transformations here as well, which I'm not going to get into the detail. Then the RNN, then in the end, the softmax for categorization. Very simple idea, and it works, by the way. Just try it. And the next thing that you can easily think of, people would like to work on this kind of stuff, that's the working on videos. Videos are both spatial and temporal signals. They are a perfect choice for CNN+RNNs. So they are easily applied to video, which is a signal sequence. So this is one of the examples, as well, famous examples. You are using a CNN, a bidirectional LSTM for CNN features. Name it LSTM with CNN features. That's a very simple name, as you can see. LSTM with CNN features, which kind of summarizes the point of it. So what they do is they have images, the first frame, then the second frame. So don't make a mistake. This is a unrolled in time representation. So you don't have many networks, guys. You have one network like this. This is the single network you have. So be careful about that. So this is the single network you have. This is, can I draw it? Yes, draw. This is the only net. No, neden çizemiyorum ya? Allah Allah. So this is the only network you use. So this is like an unrolled in time representation. This is the first frame, then second frame, then second frame. In the end, LSTMs gives you a category like diving, running, haircutting, skydiving, whatever. Simple, no difference than the previous one, right? So if you have a signal sequence, you can apply it. What are signal sequence problems we can think of? Actually, most of the engineering problems are signal sequences. If you're coming from a signal processing background, you may think of hundreds of examples. So, for example, this one, and for example, this one. Talking about signals, let's get back to usual signal processing, which is 1D signal processing, like the ECG signals. In Turkish, we say EKG. Which is like your heart signals, right? And there's this thing in heart, which is called arrhythmia, arrhythmia in Turkish, kind of the same, which is kind of a early symptom of heart attacks and those kind of problems. And actually, this algorithm is something you already have in your iWatches today, iWatch 6 or 7, I don't know was advertised with this. We can do ECG whenever you want, they said. So it is something already regular in the industry. So it's like something like face detection now. What they do is they have a CNN plus LSTM network. So they first do a type of frequency pre-processing, just like the sound signals. You did a spectrogram analysis. They kind of do some sort of frequency decomposition. That's something you always do, because in the frequency domain, signals can easily be decomposed into linear components in the frequency domain, which is called the frequency transformation, the story of Fourier transform or zip transform, or I don't know, Laplace transform. When you do this linear decomposition, it is much easier for the CNN to work on them, because separate linear components of different frequencies, orthogonal components, and you feed them to a CNN. And when you feed them to an LSTM as well, you get a result. The funny thing about this model is it is not a CNN plus RNN architecture. It's a bit strange architecture. They feed a CNN, they feed to an LSTM, this model as well. They fuse the results. That's not common, guys, but apparently these people have done experiments which they thought this way to be giving better results. I don't know, by experimentation. However, there is a very, very simple solution for this, which is CNN plus LSTM. And actually, it's very simple, guys. It is in MATLAB, this demo code in their library. So it's something very simple. I strongly recommend play with it. In Python, you also have GitHub repositories for that. But they are usually CNN plus RNNs. So this is CNN parallel with LSTM architecture. Why they have chosen an architecture like this over a CNN plus RNN architecture? Well, I recommend you read the paper. They must have a reason for that. Again, another engineering problem which has a signal sequence nature, which is classifying transient radio frequency interference. This is a fantastic study. I would have liked to be a part of this study. It is like the movie Contact. Remember the movie Contact? Like, what was that famous woman playing that? It's an old movie, you know. So she's waiting for the frequency. She's listening to the frequency, and just while she was listening to them, the aliens send signals. So it's so realistic that I'm very surprised. Whatever. So what this is, you listen to these signals, and there's always radio frequency interference, a kind of device in the usual in the world interferes with your signal. It could be a fluorescent lamp, a power tool, a transformer working down somewhere, closing or shutting off or on, or a cable. So these kind of signals actually affect the signals that you listen from outer space, because the signals coming from the outer space are very, very weak. So when you're listening to something weak, you don't want anybody to make any noises, and people make noises in the radio frequencies, these kind of noises. So it is something good if you could just differentiate those noises from actual signals coming from outer space, so that you could get a clear signal. So it is radio interference in radio astronomy, and what they use is CNN plus LSTM architecture. So they listen to the sequence of signals coming in. They get abstract features. So pieces of signals like which has an abstract representation of, for example, a fluorescent lamp coming on, or a cable interference. And in the end, the sequence classifies these noises from actual data. So if there's an interference like this, you don't listen to that part of the signal. There are endless examples, guys. One of them is stock prices, or the Bitcoin prices. People are working on it. So this is one of them. Stock price data have the characteristics of time series. People use CNN plus LSTM based models to forecast stock prices. Actually, one of your friends visited the lecture last week. Abdul Kerim, he's not here right now. Yes, he's not. He said he's working on it. The idea is simple, guys. Stock market prices are time series signals. So you first extract some features using a CNN, or maybe some frequency transformation first. I don't know, depends on your model. Then you feed them to an RNN to maybe estimate the near future value of a stock market value. I don't know. However, today, this is a simple example, but I know that there are models for this, and these models use a CNN plus RNN plus NLP technique to solve this. What they do is they have a CNN plus RNN working, but they have another branch feeding the RNN, which is a natural language processing machine that listens to Twitter. For example, it's getting counts of values from Twitter. So if in Twitter, if Tesla becomes a trending topic, it provides that information to this model as well. And there are questions. There are, I mean, industrial models that use this. And this is for Bitcoin prices as well. People are working on this. And actually, there's recently a challenge in Kaggle for Bitcoin. They provide some data. You can find data. You don't need that challenge, actually. You can download Binance data if you like. So these are very, very popular problems to work on. And this is the second time I'm giving this course, actually. I've lectured this course previously in my previous university as well. And there is at least 1 or 2 people always working on Bitcoin in their projects using a CNN plus RNN or NLP architecture. I wonder if there's going to be here today, because I strongly recommend, because that's something you can make easy money. However, I've tried myself, it's very difficult, and it needs very innovative solutions as well. So if you're considering to study this problem for stock market or Bitcoin, you're more than welcome in your projects. So what they do is they have an input layer, the sequence of time series. They feed it to convolutional layers, then they feed it to an LSTM. This is, as you can see, these are the sequences. So this is the time dimension, right? So this is the, let me write it. So this is the time dimension. This is an unrolled in time representation. And in the end, you have a value. Simple. They're all the same idea. Apply to different problems, and depending on the type of signals, with different preprocessing and with slightly different architectures. Good. Another one that you might think of applying is earthquake signals, which are type of time signals actually, but need processing as well. We are working on this with Salih Hoca from the audience, and we are working on a CNN plus RNN architecture. Difficulties in this kind of problem is it is difficult to train because you don't have much data, and the data needs quite a bit of preprocessing as well. This is a very, very new study from this year, actually, and it attracted our attention, professional attention. And actually, what these guys do is they do a strange thing. They use a convolution layer first, only convolution layer. Then they use an LSTM where they feed the signal directly to LSTM. Actually, they don't use a CNN plus LSTM architecture. And actually, remember, I've made an announcement in the previous weeks. I said, if anybody is interested in doing this thing for us, because we are currently doing this on one of our master students who is about to finish her master thesis, studied this problem in MATLAB and had some results. We want somebody to convert it to PyTorch, and actually somebody was somebody volunteered for it. She's not here right now, right? She's Elif, but not Elif Hilal, another Elif. So if she's still interested, contact us. We are going to give you the data so that you could work on it. So any type of signals. So what we are going to do, the next hour, we are going to have a live code, a long one in the next lecture. So the slides are finished. The lecture is not finished yet. So before the break, let me make an introduction to next week. What we have done today was an idea of having an encoder for spatial signals, then the decoder for the recurrency, sequential part. This encoder-decoder idea is a very common approach in today's deep learning sequence models, guys. And we are going to jump to those models next week. We are going to talk about the recurrent encoder-decoder models, where both parties recurrent, because for most sequence model problems, we need recurrent encoder-decoder models. And that idea will lead us to attention, because in recurrent encoder-decoder models, in the next week and the following weeks, we are going to realize that when we just make a relation between the states of the encoder and decoder, we could create an idea of so-called attention. And then that attention idea would lead us to the idea of context-based attention and transformers, and then we'll continue with NLP and further in the course. Okay, what to do until next week? Good. I was going to tell you this. I had some emails this week. Previous week, remember I told you that I was going to upload the project proposal, but I couldn't. It was a busy week. Now I have it. Is the project proposal. You're going to upload them to here. I've provided a PDF as a guide, very simple. So in your projects, this is what I'm expecting. Deadline is 5th of December. The deadline is 4 years because I'm not going to grade the proposals, but it is best that you have your project idea ready by then. And some information about how the report and the presentations will be. So if you apply it earlier, I can provide feedback earlier. So you can, because some of you have your projects ready because you have been emailing me that stuff. Okay, upload your proposal to class. Now, in the next lecture, I'm going to be doing live code. So I'm going to give a break now. Do you have any questions before the break? No. Okay, then let the computer record it. So let's say past 35. Okay. Okay. See you past 35. Bye.